Okay, here we're back now. We've got some space to work with here. And so let's go back to something that we did in an earlier lecture. And that was we proved that the empty set was an open set, but we did that in a kind of indirect way in the sense that we proved that the interval in the real line that was the intersection of everything to the left of 0, all the negative numbers, together with this, that the intersection of those two sets, we proved that that is open. In fact, we proved that the intersection of any two open sets is open. And of course, this is the empty set. And so therefore, we proved that the empty set is open. And I said at the time, well, we ought to be able to prove that directly from the definition of an open set, if indeed the set's open. And so let's actually do that. So let's say, let's prove that phi is an open set directly from the definition of an open set. And so let's state that. We could state it as a theorem, but I think I'd really make it a remark. It's not deep enough to be a theorem, perhaps. And that is, we're going to prove that phi is an open set. And so proof, well, what we have to prove, and so I think it's often useful to write down what we're assuming first. And here we're not really assuming anything other than, well, perhaps we could say we're in the space of real numbers, but even that's not actually necessary here. And then also to write down what it is we have to prove. So what we want to prove is phi is an open set, but that is the statement that for every, so I'm going to write down now the definition of an open set as it applies to the empty set. For every x in phi in the set, there exists a delta greater than 0 such that the ball around x of radius epsilon is itself a subset of that set. So this is the definition of an open set with phi, the empty set, playing the role of whatever notation we used for the set. In that case, it might have been S. I don't remember. It's playing the role of the set that we want to prove is open. And so let me also write this. Notice that this has the form of something we had on the screen over here before I erased it, where we said, for every x in some set, there I did say S, for every x in some set S, P of x is true. This all would be P of x, an open statement. So let me rewrite this down here, and I'm leaving a little space because I'm going to use that space. So that would be to say that for every x in phi, the empty set, implies there exists a delta greater than 0 such that the ball around x of radius epsilon is a subset of phi. So they're both the same statement. It's just that here I've rewritten this statement so that it's now an implication in which the implication is an open set with the variable x in it. And then that open statement is quantified by the universal quantifier over here. But they're the same statements. And so let's do a couple of things here. Let's note down here, let's say, that this, that's an open statement, and that has two variables in it, x and epsilon. And this is actually false for any x and any epsilon. There's no x and there is no epsilon such that the ball around x of radius epsilon is a subset of the empty set because the empty set doesn't have anything in it. So this is false for all x and epsilon. Now let's go to here. So that's an open statement with the two variables x and epsilon. There exists a delta such that this is true. Well, these are both nonsensical here. There exists a delta such that this is true. So let's fix that right now. So this should say, of course, that there exists an epsilon greater than 0. And this should say there exists an epsilon greater than 0. So good thing we caught that mistake there. Well, I guess it was inevitable we'd catch it once we start talking about that particular item. Okay, now we got it right. Okay, so let's note that this is an open statement, but the only variable, well, I take it back. This is an open statement in which both, whoa, there should have been an existence here. There should be exists an epsilon greater than 0. And so this is an open statement. The epsilon has now been quantified. So here, both x and epsilon are variables. But here in the orange rectangle, I've got an open statement where the free variable is x. Epsilon has been quantified by this existence operator. And so here I have something that is false for every x. I don't say for every epsilon because the epsilon's been quantified. It's not a variable in this orange statement here. So this is all false over here. And so now things look a little dicey for trying to prove this implication because the consequent is false. And so if the antecedent is ever true, then this implication is going to be false. It's not going to work. But of course, the antecedent here is this, and this is false for every x. So now I have in the brackets, in the green brackets here, I have an open statement which is an implication open statement with the free variables x, and for every x, the consequent's false, but the antecedent's false as well. So we're in row 4 of that truth table that we had up here, where the antecedent is false. And that's for the open statement involving x, but it's for every x. So that means that the key then is that this closed statement is true because the open statement is true. The open statement implication is true for every x. In fact, let me put that here. So this open statement is true for every x. And so the closed statement is a true statement. And so I could do the same thing up here, and I will do the same thing, but I won't do all the writing here. So let me just rewrite. Let's just do the same rectangles here and here. And here, well, there is one other thing I want to say here. And so I'm going to put this rectangle here, but I'm going to put a little squiggly rectangle here. It's sort of a rectangle. It's sort of squiggly, okay? And so here, and let's make sure that the colon here is visible. Okay, so this is not written as an implication, but again, notice that I could rewrite it as an implication down here. And so up here, everything in the orange rectangle is false for every x, just as we have down here, it's the same, okay? But this is, there's never an x that's in phi. So I can't say this is false because this isn't a statement. This is just for every x in phi. Well, that's not a statement. But we do say that this quantification is vacuous so we say that for every x in phi is vacuous. And so we say that the statement here altogether is vacuously true. So let me write that. Let's say things are getting a little out of hand in terms of all this stuff here that we've written. So this, we would say, is vacuously true. True because there isn't anything that satisfies the quantification over here. And here we would say that this, x is in phi, is vacuously true. So let me point that out here. We would say this is, well, that's not right. That's not right. That's not right. So we don't want to say that. That's not right. So we would say here that the whole statement is vacuously true, just as we've set up here. So this is true vacuously because there is no x that makes this antecedent of the open statement a true statement. So this is the proof, and in fact, we don't really have to write both of these down here. The proof is just this. That's the whole proof. It's just we have to prove this, and all we really have to do the proof is just to identify that this is false for every x in epsilon, this is false for every x, and therefore this part's false, but this is vacuous. And in fact, we don't even have to check whether these are true or false, because if this is vacuous, it doesn't matter what's over here. The whole statement will be true. We can see that down here. Since this is false for every x, it doesn't really matter whether things over here are true or false. It doesn't make any difference, because if for every x this is false, then this implication is true for every x, whether that's true or false. So the key to the proof is exactly that this is vacuous. There is no x in the empty set. After that, this turns out not to matter. So this is a typical, although much of the simplest kind of, you'll often see this referred to as a vacuous proof. I think that's bad terminology. The proof isn't vacuous. The proof is meaningful, okay? So the proof isn't vacuous, but it's proof, you could say proof by vacuousness, or proof using vacuousness. And the proof goes by showing that we have a statement that is vacuous, or a quantification that's vacuous. So that gives us a proof directly from the definition that the empty set is open, and this is not just going to happen with the empty set. This is something that happens fairly regularly. We'll see this again, I think, in the course, I'm sure, because this is a common occurrence that we have a proof, what I would call proof by vacuousness. Okay, so let's now take this off, and we'll do one more result, a theorem that we have done already in a theorem that we've already done in a previous lecture. So we'll take this off, we'll be back in just a moment.